Okay, everybody, welcome back. So we just left off, I believe, with the polytropic process. Yes, and that concluded our review of thermodynamics for lecture 1. Now, in lecture 2, what we're going to focus on is the Reynolds Transport Theorem, which is basically a synonym for control volume analysis, but forms the basis for a lot of very important thermodynamic relations and conservation equations. So we'll go ahead and write that down, the Reynolds Transport Theorem. And okay, we'll eventually get to that, but before we do that, let's talk about flow dimensionality. Okay. So the first bit that we need to discuss before we dive into this topic of flow dimensionality is we have to talk about the material derivative. So what is the material derivative? It's also often called the total derivative. And it's defined in the following way, usually written with a capital D. In this case, we'll talk about pressure. So capital dP dt, okay? And the way it's defined, and I'll use vector notation first, is that you have the local derivative, dP dt, the local partial derivative with respect to time of the pressure, plus the gradient of the pressure, okay, dotted with the flow velocity of the mass. Okay, and the way that you write that is you dP dt can't be simplified, of course, but we then when you write out that dot product, you have dP dx times dx dt. So notice that the dP dx is a partial derivative, and the dx dt is a total derivative, and that's because it's the derivative of a dependent variable. The dx dt itself forms a new dependent variable of the system, and then it's d del p del y times dy dt plus del p del z, partial derivative of pressure with respect to z, times dz dt. Okay, so like I said before, this part here is just the local time derivative. And then this chunk here is what's referred to as a convective derivative. Okay, so what does this tell us? Well, the material derivative, or the total derivative, tells us what the rate of change, it tells us the rate of change of a property, in this case P, at a point that travels along the flow. Okay, so let's think about this for a second. So imagine the flow is not moving. The pressure can still change as a function of time. Say if you're heating up the fluid and it's quiescent fluid, right? So in that case, you just have a local time derivative. But if the flow is moving and you have a particle that's traveling along with the flow, it might move from a region of high pressure to low pressure, even though the overall pressure field in the fluid is not changing with time. So let me show you what I mean by that. So like let's just draw a little pressure field, a 1D pressure field, meaning so you have pressure here, and it's a function of just x, some in one direction. And then let's say we have this curve at t equals t naught, and then we have another curve that joins up with the first curve, and this other curve is at t equals t1. Okay, and so if you're at, let's say this red point here, right? Your local time derivative of the pressure is actually 0, but if the flow is moving, if you have some component of the flow that's moving in the u direction, so let's say you have like your flow velocity v is going in this direction, then in a unit of time you'll move in this direction a little bit, and your pressure will change to be this value now, right? And so that new value you can calculate. It's just the change in pressure in the time that it took you to move that amount is going to be the change in pressure over that space multiplied by how fast you travel through that space, right? And so that's really all the convective derivative is it's just accounting for change in a property as you move through the property. And then of course you could have both going on at the same time. The overall underlying pressure field could be changing and you could be moving through the fluid. So that's why the material derivative describes the rate of change of some property at a point that travels through the flow. Okay, so in general, the velocity field of the flow velocity, is itself a function of all three dimensions and time, right? It's a function of x, y, z, and time. X, y, z, and time. Okay, but in most cases of this course, we're actually going to have a much simpler case. So first of all, in most cases for this course, oops, that's not how you spell course. In most cases of this course, we'll be considering steady flow. Considering steady flow. What does steady flow mean? Okay, steady flow is completely interchangeable with the statement that the operator d by dt is equivalent to 0. So anytime you take the partial derivative with respect to time of something, it just goes to 0. It's the same as multiplying by 0. Okay? Likewise, we will often be considering flow through channels and pipes. Okay, and typically something that you might remember from your fluid mechanics class is that when the flow is laminar, okay, that would be for low Reynolds number or slower flows, okay, the flow profile in the pipe, let's like take the example of a cylindrical pipe, okay. The flow profile or the velocity profile in the pipe would be something like a parabola, right? So all the fluid streamlines are parallel, and this is like your flow velocity, right? Okay, and then if you were to write out what that velocity profile is, it would be like v is equal to v mean, or the mean velocity, times 1 minus r over r naught squared for a cylindrical pipe. Okay, it's parabolic in r. And then the mass flow rate, you would evaluate as an integral in cylindrical coordinates from 0 to r naught of rho u 2 pi r dr, where you plug in, sorry, not u, v is what I named it here, rho v 2 pi r dr, and that would give you just rho a being the cross-sectional area, which would be pi r squared, times v mean over 2. Okay, so that's stuff that you probably saw in your fluid mechanics classes, coursework. But in most cases in this class, we're actually going to be dealing with turbulent flow because we're going to be at such high flow velocities, Mach numbers exceeding 1. Okay, so for turbulent flow, the velocity profile in the channel or pipe is actually a lot more flat, because a lot of say turbulent dissipation happens near the walls, and then you reach this sort of core of the flow that's very uniform in the middle. So what it might look like is something like this, where you have a very kind of almost uniform flow in the middle, and then very strong flow velocity gradients near the edges. But what that means is that we can kind of look at the velocity profile in this flow as though it is uniform. Okay, so we can write that down. This is sort of like an approximately uniform velocity profile within the pipe. Okay, so we assume that the profile is approximately flat, and so what that means is that the partial derivative with respect to r, so as you move in the radial direction, and the partial derivative with respect to theta are both 0. Again, using cylindrical coordinates here, but the same would be true of a square duct. It would be the two directions that are perpendicular to the direction of the flow. Okay, like the cross-sectional area, the two directions that span the cross-sectional area at any point in the channel. The partial derivatives in either of those directions go to 0. Okay, so for that reason, so imagine we have steady flow and it's turbulent. What you end up with is that you only have variation along one dimension. So like for this up here at the top here, we had x, y, z, and t. Imagine z is the direction along the length of the pipe. What we've shown is that for turbulent flow, there is no variation in x or y, and there's also no variation in t because we're assuming steady flow. And so we say we're left with our velocity field being just a function of z only. And this is what we call one-dimensional flow. Okay? So you might have you can still have variation along z. So like we will examine cases where the cross-sectional area A may be a function of z, for instance. So that's why the flow velocity field might change as a function of z. Okay. So one important note here is that one-dimensional is not the same thing as unidirectional. So what do I mean by that? Well, what I mean by that is that 1D steady flow simply means that at a given cross-section of the channel or pipe, d by dt and d by dr and d by d theta are all equal to 0. But the duct could change direction. So you could have a duct that turns upwards in this way, right? And the flow is going and changes direction with the duct. But at a given cross-section within the pipe, you still have one-dimensional flow, okay? Even though the flow is changing direction. It's varying as a function of the distance traveled along the length of this pipe, okay? So just keep that in mind. If you're looking at one-dimensional flow, it is not the case that it is unidirectional. You might have changes in direction, okay? So now let's go ahead and dive into control volume analysis now that we've really established what 1D flow is. Control volume analysis. I think I'll start highlighting sections in green here. And we'll start doing definitions in yellow. I should have been doing this before. Okay, so control volume analysis. Let's define a couple things, okay? So we're going to define N, okay? Just for the purpose of this class. It's going to be a little overloaded because N can also mean total number of particles, but I don't think that we'll be using that very often. N will be defined as the total amount of a given extensive property. Think of something like mass or energy or momentum, for example. Okay? And then eta is going to be defined as the amount of N per unit mass. N per unit mass. Okay? And so, putting that together, we can express N as an integral of eta over the control mass. So, say this is like some sort of volume integral here, where we're integrating eta dm, okay? Another way you can express this is sort of as a triple integral to make it less opaque, and we could have eta times rho dv, okay? Now integrating over volume times rho, because that's the same thing as dm. Often though, what I'll do is I'll just write this as like integral with some sub v or something, some sort of subscript to tell you that you're doing an integral over an entire volume or control mass or something. And you'll just write this as rho eta dv, okay? So what we're going to do, what we're going to try to develop is an expression for the total derivative of N, which is, again, just the total amount of a given extensive property. So let's find an expression for dN dt, which by definition, by the definition of the derivative, is equal to the limit as the change in time goes to 0 of n at t plus delta t minus n at t divided by delta t. Okay. So what we're going to do to develop this is we're going to consider a control mass. Okay. Just kind of a blob of material. Okay. The hard line is where the control mass is. And then, that's the control mass at t equals t naught. Okay. And then we'll say that sometime later, the control mass has moved and perhaps even deformed to this location denoted by the dashed red line. Okay. And this is at t equals t naught plus delta t. All right, and we're also going to define a control volume. And the control volume is what encapsulates the control mass at t equals t naught. Okay, and the control volume is denoted by this green dashed line. Okay, so the green dashed line is the control volume. And then we'll also define these regions. The region that contains, that is sort of contained by the red and dashed line on the left is region 1. The region of overlap between time 1 and time 2, say, is region 2. And then the region where the control mass is occupying new space is region 3. Okay? So what we can do is we can actually split up this dn dt derivative into a few different pieces, right? So based on this diagram, dn dt is equal to the limit as delta t goes to 0 of n2 at t plus delta t plus n3 at t plus delta t minus n1 at t minus n2 at t. And then that whole thing divided by delta t. Okay, so n2 plus n3, that's the amount of n in this region here and this region here, is indeed the total amount of n, or the total amount of n in our control mass at t plus delta t after it's moved, and then likewise for n1 plus n2 at time t, which is t naught. I really should actually include the subscripts here. So these should be t naught and t naught and t naught, t naught, to be precise here based on how I've defined the times at which those are occurring. Okay, all right, so what we're going to do is we're actually going to hunt down these sort of N2, N3, and N1 at different times so that we can get this expression for dn dt. General expression for the time derivative of the property in that control mass. So we'll start by writing down the amount of the property n that leaves the control volume CV in our time step. Okay, it's approximately equal to, and equality would occur in the limit that the delta t goes to 0, of course. but it's the integral over S out, okay? And S out is the surface, the portion of the control volume that the control mass passes out of, okay? So if you integrate over that S out surface of eta rho times V, which is the flow velocity of the medium or of the control mass material, dotted with n hat, okay? I'll talk about what n hat is in just a moment, dA times delta T. Okay, so what is n hat? N hat is the outward normal of the control volume. Okay, so if you take the velocity of the mass that's passing through the control volume boundary, and you take the dot product of that with n hat, that gives you an idea of the rate of that material crossing the boundary. Okay, and the reason why you need the dot product is because you're concerned with the flow directly out of the surface. The tangential component of the velocity at the surface is not causing any flux of the material out of the surface. So by taking the dot product with the outward facing normal, you're zeroing out or focusing only on the material that is leaving the control volume. Okay, and then I'll also label this S out thing. So we're integrating, even though I've said it before, we should write it down. This is integrating specifically over the surface where the control mass Cm crosses the control volume boundary, Cv boundary. Okay? So we can divide both sides by delta T. Okay, so again, what is the amount of n that leaves the Cv and delta T? Well, that's precisely n3, right? It's the amount of n that's in region 3. So we can divide both sides by delta T, and we can say that this is n3 at T plus delta T divided by delta T, and that's approximately equal to the integral S out of eta rho times V dot n hat dA. Okay. Okay, and then if we took that limit to of delta T going to 0, what we would actually obtain is dn3 dt in the limit. And the reason why that is the case is because n3 at t naught, right, at the initial time, is equal to 0. So you can say that this is, you can add a little n3 at t here, minus n3 at t, since that whole thing is equal to 0. I'll erase this in a second. And then you just have the definition of the derivative. So you take the limit as delta t goes to 0, then you just recover the total derivative of n3 with respect to t. Okay. Just as a note. Okay. All right. So that's the amount of n that leaves the CV. That sort of takes care of n3. Okay. How about the amount of our property n that enters the control volume? Now this is a little funny to think about because we've been focusing on this control mass, okay, and where it ends up, but in the space that it vacates, there's more material, which I'll draw in here with blue lines, that has to sort of flow in to fill region 1, right? at the later time. So the amount of n that enters the CV is a integral. In this case, we'll write it as S in. Okay, so that's the surface over which material flows into the control volume, and it's going to be rho eta and v dot n hat dA times delta t. Okay, and importantly, we need to place a negative sign here because we're still using the outward normal n hat, and that's anti-aligned with flow that's coming into the surface. If the surface is here and you're looking at flow coming in, the outward normal is pointing this way, then that anti-aligned is going to make you pick up a negative sign. But because we want to account for the amount of flow into the control volume and want that to be positive, we need to apply a negative sign to make the signs work out there. And why do we even care about this flow into the control volume over S in? Well, we're talking about the flow that replaces the property n that left region 1. Region 1 was formed by the control mass's initial position, and then that material flowed out into regions 2 and 3, but more fluid was carried into that void. And so we can calculate the amount of n at time t divided by delta t by performing this integral of how much of the property n was carried into into region 1 or into the control volume in the space that was vacated by the material during this passage of time. Okay, so we pick up that negative sign. Okay, and so that's another piece there. Let's also consider the change of the property n in region 2. Okay, so now we're not following the mass, right? We actually want to look at the limit as delta t goes to 0 of n2 at t plus delta t minus n2 at t divided by delta t. And this is equal to, oh, this is actually a little bit of a revelation here. So what this ends up being equal to is actually the partial derivative of n2 with respect to t. Okay, so first of all, why is this a partial derivative? Okay, why partial? Well, it's because we're not following the mass anymore. We're looking at a defined region. So not following mass. Looking at defined fixed region. Okay, and furthermore, why is it derivative at all? Well, I mean, it's in the definition there, right? You're basically have the definition of the derivative, but like I said, we use a partial derivative here instead of a total derivative because of that, the way we're defining this. Now, one conceptual leap that we have to make here is that we have to note that as delta t goes to 0, region 2 approaches the control volume. Okay, so what's happening here? So imagine this picture here that we're looking at on the screen. As delta t goes to 0, that dashed red line is shifting over as you shrink delta t until it eventually will lie right on top of the solid black line and be coincident with the control volume, right? So, and we're evaluating all of this in the limit as delta t goes to 0. So in that limit, the region 2 approaches the CV, so we can represent N2 as just, in this limit, we can say that N2 is equal to NCV, meaning that the amount of N in the CV, okay, which we can write in the following way, where we do the partial derivative with respect to time with an integral over the CV. That's what this subscript here, integral over the CV of eta rho dV. Okay, so we can replace these terms, the N2 at t plus delta t, t naught plus delta t rather. I think I left it. We did replace this with a naught as well. Oops, sorry about that. We need to replace this with a t naught as well. Let me get the zoom right here. Okay, and I guess I dropped one right there too. Right, so that those two terms get replaced with this guy right here. Okay, so now all our terms are actually accounted for in this equation right here that we were looking for. Okay, so we have all the pieces that we need, and we get the following expression, which is that dn dt is equal to the partial derivative with respect to time of the integral over the control volume of eta rho dv. So that's that piece that we just found, plus the integral of s out eta rho v dot n hat dA, and then here we had this was n1 at t naught, right? So we get this minus sign gets canceled out, right? So this minus sign cancels with the one up here in the expression, and you have plus the integral over S in of eta rho v dot n hat, the outward normal, dA. And now you have the same integrand and the unification of the surfaces S out and S in. If you add both those surfaces together, you just end up with the entire control surface, or the entire volume of the control volume, or the entire boundary of the control volume. And so you can replace that with a single integral. So the first piece is the same. You integrate over the entire control volume, eta rho dv plus, and then now we just say we integrate over the control surface this eta rho v dot n hat, the outward basic normal, dA. Okay, and then this equation here, which I'll frame, a la Lazzati, is known as the Reynolds Transport Theorem. Okay, it's essentially a conservation law, to put it simply. And like I said before, it's a starting point for many types of fluid mechanics analyses. Okay, so let's go ahead and work with this theorem a little bit. So what can it tell us? What kind of equations can we develop? Well, let's start with just conservation of mass. So in conservation of mass, eta just simply becomes 1, because our extensive property that we're trying to track is the mass itself, right? So let's see, we don't have any relativistic effects here. Since we don't have any relativistic effects, we know that we're always just going to have that the total derivative of the mass as we follow the mass around is equal to 0, right? Mass doesn't change. Mass is conserved. And this is actually known as the continuity equation. If we sub this into the Reynolds Transport Theorem, letting eta, and remember we have eta equals 1 for this case, then you end up with 0 is equal to d by dt of c over the cv, or your control volume, rho dv, because eta is equal to 1, is equal to, or sorry, plus the integral over the control surface of rho times v dot n hat dA. Okay? So that's the continuity equation for a control volume. Okay? One example here. Say you have steady 1D flow in a pipe, and we have our pipe right here, and we define our control volume in the following way, where the left boundary is just sort of far off in the distance to the left, and then at the right boundary here we have a uniform velocity profile at a magnitude of v, okay? And we have a known cross-sectional area A. Okay, so if we the flow is steady, right? So now let's use this continuity equation for the control volume that we just derived, and we have 0 on the left-hand side. The partial with respect to t of rho dv, this term goes straight to 0 because it's steady. So the partial derivative, any partial derivative with respect to time goes to 0, and then you just end up with this integral cs rho v dot n hat dA, right? And so the way this is set up, this ends up just being rho times v times a out minus rho times v times a in, and then this becomes true regardless of the in and out surface here. Okay, this case or this result, and what this is telling us is that that rho AV, otherwise known as the mass flow rate, as you might have seen in your fluid mechanics course, is constant. Okay, so for 1D steady flow, the mass flow rate is going to be constant. All right, and you will use that fact quite often in the class. All right, let's talk about conservation of energy. I usually also highlight the examples in pink there. So conservation of energy, whoops. So in this case, eta becomes lowercase e, which we said before is like u plus v squared over 2 plus g z. Okay. Now, what does does the first and second law, or rather the first law of thermodynamics, tell us about the total derivative of energy, right? It tells us that dE dt is equal to the partial derivative of q with respect to t minus the partial derivative of work with respect to t. Okay. Again, keeping in mind that these are path functions here, so it's kind of these are weird derivatives, but still the same idea. So the way that you, in fact, there's actually a notation style here that you can use where you use the curly delta up top and then a straight delta on the bottom to make it very clear that these are instantaneous rates of energy transfer across system boundaries. System defined by CV, of course. Okay, so let's just be really explicit about that. So we can write this as d by dt over control volume of E rho dV plus the integral of the control surface E rho, same story as before, v dot n hat dA. Okay? So what can we use this relationship for? Well, let's talk about shaft or pressure work. Okay. Okay, so if we have another duct here with a cross-sectional area A, and we have, our control volume in the center of this duct. And let's say we have a propeller that is injecting energy into the flow at a known rate, delta WC dt. Okay, so we have this injection of work. So there's also two different types of, there's an additional type of work that's being done at the boundaries of this system here, right? So we have the propeller. That's one way that we're getting energy injected into the system. But there's also the pressure at the control volume boundary that's pushing the fluid in and out, and that is work being done. Okay, so we can write that down. Pressure at the CV boundary pushes fluid in and out. Doing work. Okay, so what do I mean by that? We can denote this, say, delta WP. In general, we can sort of denote our work, incremental work done, as F times delta X, or dot product of F and delta X. F in this case is P times A, where A is oriented in the inward normal. Okay, dot product with V, delta T. Okay, and then if we take the limit as delta T goes to 0, delta T goes to 0, then we end up with our rate of pressure work transfer of delta WP dt is equal to P A V, which you can rewrite as m dot P V using specific volume. Okay, and then what that leaves us with is it allows us to calculate a heat transfer rate, or solve for a heat transfer rate in the following way. So leaving us with the following, which is delta Q dt. So again, we're solving for that. And then we have that given amount of shaft work, dt plus partial with respect to t over your control volume, E rho dV. Okay? Plus, and then this is the sum of all those pressure works. And as well as the internal energy being carried in and out of the system, right? PV. Okay, and then this sum I is like the sum sort of in/out surfaces. Okay, so because this is 1D flow, I'm just breaking it down to a mass flow rate multiplied by the property at those surfaces. I should put a subscript on these guys too, because those change at each surface. Okay, so the flow is carrying a certain amount of energy out. That's what the lowercase e is. And then the PV, the m dot PV, that's that pressure work that we just worked out. Okay, so that's what that whole right-hand term is. And then the other simple local time derivative term is just adding up the time rate of change of the energy in the interior of the control volume. Okay, and so now we're going to define a couple things. So next, define Q, which we'll define as 1 over m dot delta Q dt, and lowercase delta, or omega, or sorry, lowercase ws, which has to do with that shaft work, 1 over m dot delta ws over dt. Okay, and then this is, the units of this are actually just joules. Okay, so it's a bit of a weird quantity. In words, it's the rate of energy, and RG is short for energy in my shorthand, rate of energy flow per unit mass flow. Oops. Okay, so it's basically just energy transferred per unit mass. Okay, but there's just like this, it's rate of energy flow per mass flow. So it's but it's just energy transferred per mass. But yeah, so let's assume that we're in steady state and replace these or substitute these definitions in. We end up with Q is equal to Ws plus U plus V, I'm just expanding the definition of E here, plus GZ plus P times V out, minus that same quantity U plus V squared over 2 plus GZ plus PV in. Okay, and then what we can just write this as H in. Okay, so we're going to replace U plus PV with the enthalpy. We can write this as H in plus V in squared over 2 plus GZ in plus Q is equal to H out plus V out squared over 2 plus GZ out plus WS shaft work. Okay, and this is like our energy equation for steady 1D flow. Energy equation, steady 1D flow. Okay, so keep this one in mind. I'll even frame it because it'll become useful later. Or equivalently, we can also just write this in differential form, because this is essentially telling us that these are all just small changes, right? So we can write this as in sort of a differential form, as keeping in mind that Q and or heat and work are path functions. We have the following relationship: d v squared over 2 plus g dz. Okay, that's just essentially. There's a more rigorous way to define that and to derive that, but you can just imagine that you're essentially just subtracting both sides and taking limits there. If you want to hand wave it around, I think there's a more precise definition in the textbook. Okay, so cool. So now let's actually try and decide if we should do momentum or entropy first. Let's talk about entropy first. So that was a bit of a, so what we did there is we used the Reynolds Transport Theorem to come up with an equation for an energy conservation equation, okay? In both, in differential form as well. So now let's talk about entropy. Okay, so I want you to recall that from your thermodynamics coursework, that you can split a change in entropy into the entropy due to reversible process, change in entropy due to reversible processes, and the change in entropy due to irreversible processes, right? So this is entropy produced by irreversibilities. So, and then this is the bit that's the same as like delta Q over T, right? So that's the path independent part that Clausius defined. So like in this case, you can take a moment and remember Clausius's inequality. Clausius, where the total integral of ds is less than or equal to 0 for a closed property, for a closed process, and that's because we have that dsi is sort of greater than or equal to 0, right? For the surroundings, I should say. Okay. Okay. So let's talk about adiabatic processes for just a second. So an adiabatic process, meaning there's no heat transfer, dse is equal to 0, right? Because there's no heat transfer. Delta Q is equal to 0. And then a reversible process means that dsi is equal to 0. So then an isentropy process is both adiabatic and reversible. Okay. So let's sort of take a step back to that fundamental thermodynamic property relation where we had T ds is equal to dH minus V dP. Okay, we derived that in the last lecture. We can split up the reversible and irreversible part of the entropy, and get the following, where we have T dSE. This whole thing here is the same as delta Q, right? Is equal to dH minus T dSI plus dP over rho, since the specific volume is just 1 over rho. Apologies for the allergies. Okay, so let's combine that with the differential energy equation for 1D steady flow that we found before. So this box thing at the top of the screen, let's substitute in this delta Q that we just found, right? And what we end up with is the following. So let's write the left-hand side of the equation first. So let's say sub into differential energy equation. And what you get is delta Ws plus dH plus d v squared over 2 plus g dz is equal to, and this is where we sub in the what we found for delta Q, which is dH minus T dSI minus dP over rho. Okay, and then the enthalpies cancel, and what you end up with is dP over rho plus d v squared over 2 plus g dz plus t dSi plus delta Ws is equal to 0. Okay, and this is another important equation that is called the pressure energy equation. One thing is that you actually can recover from this equation, you can recover Euler's equation if you assume no shaft work and no irreversibilities. So if assume no Ws or dSi, then recover Euler, which you can integrate to Bernoulli's equation. I'm sure Euler is just the Euler equation just describes ideal flow, and then I'm sure you've seen Bernoulli's equation if you've taken any fluid mechanics at all. Okay, one more thing. We'll talk a little bit about momentum, and then we'll be done. Once again, this took longer than I expected. Okay, so last thing that we will apply the Reynolds Transport Theorem to today is momentum. So in this case, what is eta? Eta is a vector quantity v, since momentum is m times v, right? So the amount of momentum per unit mass is just the velocity. Okay, so what are we talking about? We're talking about linear momentum. And since we're talking about linear momentum, we can invoke Newton's second law, which tells us that the sum of the forces acting on your system or object is equal to the time rate of change of the momentum of that control of that system or object, right? And so in this case, we can sub this into the Reynolds Transport Theorem and say on the left-hand side, what we would normally have is dp dt, the total derivative of the momentum, P being the vector piece of momentum here. And what you end up with is the sum of the forces acting on the control mass or system is equal to the partial derivative with respect to time of the integral over dv of rho v plus the integral over control surface rho v times v dot n hat dA. Okay, and this we call the momentum equation. This bit here, this v and v, the two different v's here are not the same v. Okay, so this v is, I'm going to put in a little subscript here, like VCS. This is the v, the velocity relative to the control volume boundary. Okay, and that can be important in problems where you have, let's say, multiple moving parts, and you might have your control volume be moving, okay, with respect to your lab frame or whatever frame you're using to measure the velocity. And you really have to take that into account when you're doing those problems. Okay, so a word of warning to take that into account. All right, you'll likely see a practice problem, or perhaps even an exam problem that that has to deal with that case. Okay, so let's look at an example. In this example, we have 1D steady flow through a channel. And we're going to relate 2 points. So we'll put our control volume here. Let's say we have point x1 and point x2. The x direction, of course, is moving to the right. We have some flow velocity going to the right. And then we also have some force of friction acting on the channel walls. Okay? And we have a known cross-sectional area A. Okay? So let's write down all of our forces. First, of course, we have the pressures, right? The pressures at points 1 and 2. The pressure acts inwards on the control volume. So P1A minus P2A, okay, that gives you the right directionality for those pressures opposing each other. And then we also have this force of friction. Okay, and then it's steady, so we don't have the partial with respect to t term, but we do still have our surface integral term, rho v dot n hat dA. In this case, the v's are the same, so we don't have to worry about that note that I made before. But we do have to be careful about our signs. So at point 1, the outward facing normal is anti-aligned with the velocity. So you pick up a negative sign. You have minus rho 1 a1 v1 squared, and then at point 2, they're aligned, so you don't pick up a negative sign. So you have rho 2 a2 v2 squared. Okay, and then you can see that you could express this as m dot times v2 minus v1. Okay, and that's just because rho 1 a1 v1 is the mass flow rate at point 1. However, the mass flow rate is the same at point 1 and point 2 because of conservation of mass, right? We proved that before. So that's why you're able to just pull out the mass flow rate there in that equation. So let's see. Okay, so then you have this expression here. Now, what I'm going to do now, instead of taking the time to derive this, I'm just going to sort of drop this on you. It's derived in the textbook between pages 76 and 80, is the differential form of the momentum equation for steady 1D flow. So diff form of momentum equation has the following form. You have dp over rho plus F. F is the friction factor times v squared over 2 dE. dE is an equivalent diameter. dx, I'll label these in just a moment, times g dz plus dv squared over 2 equals 0. Okay, once again, this is derived on pages 76 through 80 of Zucker and Biblar's. Okay, this was friction factor. And this is equivalent diameter. Okay, this is, you can express this the following, where you have 4A cross-sectional area divided by P, where P is the perimeter. Okay, almost done here. And the friction factor, to expand on that, is equal to 4 tau wall over rho v squared over 2. Basically relates the shear stress at the wall to the dynamic pressure. Okay, in our texts, uses a factor of 4. So one thing the reason why I brought this up after doing that short 1D steady flow example, which actually leads to this differential equation just after more derivation work, is that I wanted to note the similarity of this equation with the pressure energy equation. So if we compare the same terms, the pressure energy equation, say, is the following. So here, I'll reproduce it really quick. Sorry. So note similarity with the pressure energy equation, which said dP over rho plus dV squared over 2 plus G dZ plus T dSI, right, that irreversible entropy term, plus delta S equals 0. So let's look at this in the case where we have no shaft work, right? If we have no shaft work, what you end up with is that, so you say no work, sorry, so no work, in that case you have that T dSI is equal to F times V squared over 2 dE dx. And what this tells us is that friction is a source of loss or entropy production. Friction is a source of loss / entropy production. Okay? All right, so that brings us to the end of this lecture. Sorry, I got a little stilted at the end there, but the point is that you use the Reynolds Transport Theorem here. Okay, you use it, you input different quantities like mass, momentum, energy, and it allows you to come up with these very useful conservation equations, like that for a steady 1D flow, the mass flow rate is constant. Okay, or in this case, you get this energy equation And then here we ended up with a pressure energy equation that after we came up with this 1D steady flow through a channel in this case, which eventually leads to this differential form of the momentum equation, we could compare the two and come up with some physical insight in this case that the friction here is leading to entropy production. Okay, the two are essentially equivalent. Okay, so that is it for this lecture. The next lecture, we're going to actually start to get into some compressible flow. So consider this lecture a bit of a fluid mechanics heavy lecture that picks up that other leg from the thermodynamics review that we did in the first lecture. And then next lecture we're going to really jump in and let's see, we will even we'll derive the speed of sound and talk about the Mach number and a bunch of other interesting topics. So stay tuned. Thanks for tuning in to this lecture, and I will see you next time.